Hi, I want to continue our discussion on reaction mechanisms. In this video, we are going to consider a reaction in which the first step is not the slow step. The first step in this case will be fast and reversible. How do we get the rate law expression for the overall reaction if the first step is fast and reversible? Just a reminder, in a previous video, I went over the case where the reaction mechanism where the first step is slow. That's the easier of the two situations, because if the first step is slow, then the rate law expression for the overall rate, oh my goodness, the rate law expression for the overall reaction is identical to the rate law expression for the first step. And here's an example. Here's the example. Because the first step is slow, the rate law expression for the overall reaction is identical. Okay. Are we ready to try the harder example? The hard example is if the first step is not slow, if the first step is reversible and fast. We're going to jump right into it. Let me give you the overall reaction. We are going to look at another one that has nitrogen oxide plus Cl2 gas goes to 2NOCl gas. And I want to know the rate law expression for that reaction, given that step 1 is proposed to be NO gas plus Cl2 gas. I just want to make sure I'm doing this correctly. Equilibrium is this kind of single barbed arrows, one to the right and one to the left. That means it's reversible. The product is NOCl2, so it's not the overall product. That's the gas also. And this step is fast. Fast and reversible. Step 2, we're going to take this NOCl2. Do you remember what that's called? The molecule that shows up in an earlier step produced and then later consumed? That is called the intermediate. And then we have one arrow this way. This is the slow step. 2NOCl gas slow. And you notice that when you add these two reactions, we do get the overall reaction, I think. Those cancel out, and we have the overall reaction right there. Okay, this is a plan. Because the first step is not the slow step, we cannot take the rate law expression for this reaction and make it equal to the rate law expression for this reaction. But let's practice. In step 1, right, the rate law expression would be what? Rate equals K times the concentration of NO raised to the power of 1. So you do use the coefficients for the, what are these called again? These are elementary reactions. Times the concentration of Cl2. But that's the fast, oh, wait a second, that's the fast step. Yep, that's the fast step. For step 2, the rate equals K times the concentration of NoCl2 times the concentration of NO. Just give me 1 second. My cat's scratching up my carpet. Okay. If the step 1 is slow, then the overall rate law expression would be this exactly. But it's not. This is the slow step. The problem with this is that we cannot use this directly as a rate law expression for the overall, because this molecule right here is not a reactant of the first, sorry, it's not a reactant of the overall reaction. We have to replace it, the term. Okay, let me write, oh man, you don't see that. NaCl2 is an intermediate and it's not a reactant of the overall reaction. So the question is, what is the rate law expression for the overall reaction? The idea is to take this rate law of the slow step and figure out a way to replace NaCl2. Kind of tricky. So we are going to use the fast and reversible step. So I'm writing these steps down. Take the fast and reversible step, and it's the reversible first step. All of this would have been unnecessary. All of this, what I'm about to do, would be unnecessary if the first step was the slow step. If the first step was the slow step. Okay, so you take the fast and reversible first step, and you write the rate law for the forward direction and the backwards direction. So we'll call this K1, and this is K minus 1, going in the backwards direction. So there's a rate associated with the forward direction, and there's a rate associated with the backwards direction. So in the forward directions, we have a rate of the forward, FWD, equals K1 times the concentration. Do you see what I'm doing here? Concentration. Let me zoom out a little bit. My bad. Okay. What is the rate law for the forward reaction? Concentration of NO times the concentration of Cl2. The thing is, when it's at equilibrium, the forward rate is identical to the backwards rate. Okay, so here we have the rate backwards. Oh, let's use the word reverse. Equals K minus 1. Okay, so now we have to go in the opposite direction. Pretend that's your reactant, NoCl2. Do you understand how I got these two rate law expressions? The rate in the forward direction for step 1. So both of these are step 1. The reversible step. Okay. The rates are identical. They have to be, or else it wouldn't be at equilibrium. Okay. Equilibrium meaning that the amounts of each of these three are now static. They are constant. Okay. All right. So since they're identical to each other, we're going to set them equal to each other. All right. So we have K1 NO Cl2 equals K negative 1. Don't worry about what the K's are. All K's are constant. Now they're not identical. They're not identical, but they're constant. Again, what is the goal? The goal is to replace that term right there. To replace the term in the slow step that is not part of the overall reaction. NoCl2 is not in the overall reaction up here. Okay. See, we have it right there. So what are we going to do? We're going to bring over the K. The interesting thing about these k's, the k forward, the k backwards, these are rate constants, is that a constant over a constant equals another constant. And that's how we're going to get rid of all of these different constants, because they're all going to conglomerate and be one overall constant. But anyway, we have this. NoCl2 equals the concentration of NoCl2. You see how we could take that stuff right there and just smack it right where this concentration is? That's great, because now these two compounds are reactants in our overall reaction. So we are going to take this term and replace it. So recall, let me scooch up here. Recall that we had the rate law expression for step 2, which is rate equals K times NoCl2 times NO. And we are going to take all of this here and replace it for that, because they are equal to each other. See, that's equal to that. All your k's will just conglomerate into one giant k, into a different k. So we do have k times k1 over k minus 1 times the concentration of NO, concentration of Cl2. So that's the replacement. But also we have this NO from our original rate law expression for the slow step. So here we have NO. That NO down here is this NO over here. So then we just simplify, okay? All the constants, a constant times a constant divided by constant is just a constant. And it doesn't really matter to me whether you have a subscript. It's still a constant. So typically you just put K. We have NO twice. That means it's NO squared. And then we have Cl2. What we were able to do, this is the answer, by the way, for the rate of overall reaction. And we should say the rate law of overall reaction. What we just did now is we took the rate law expression of the slow step and we expressed it in terms with reactants that are in our actual overall equation, overall reaction. And by replacing that term, that concentration, with this here, we were able to get the rate law expression of the overall reaction. Now, yes, those of you who have eagle eyes notice that the exponent 2 is the same as the coefficient 2. And the exponent 1 is the same as the coefficient 1. That's just a, that's real. But for a lot of other problems, you do understand that the m and the n, the exponents, will not match the coefficients. So we can't always assume that. In this case, it did work out that the coefficients did match the exponents. But again, you were taught that m and n, the exponents, do not directly come from the coefficients. And there are many cases where they do not match. They do not match. So just keep that in mind. But in this case, they do. Okay? Does that sound good? So, I want you to do at home. I'm not going to show you how to do this on the video. I might have this as a problem for one of my classes. Look at this problem here. And go ahead and copy it if you want. I'm not doing this on the video. Show all your work. And yeah, they want the rate law expression for our overall reaction based on the two elementary reactions shown. So if we add these two elementary reactions, they will equal the overall reaction. And in this case, NOBr2 is the intermediate. The slow step is not the first step. If the slow step was the first step, then the rate law expression would have been rate equals K times the concentration of NO times the concentration of Br2. But in this case, the slow step is the second step. So we do have to do this sort of substitution, because the rate law expression for the slow step includes a molecule that is not in the overall reaction. So the strategy is write out the rate law expression for the slow step and then do your manipulations to replace NOBr2 by using the fact that the first step is reversible and fast. That understood? Okay. I'm going to show you the answer. If you don't want to see the answer, stop the video right now. I'm going to show you the answer, but I'm not going to show you the work. That's what I'm going to have my students do most likely. The answer is this. NO squared times Br raised to the 1. Okay. Now, sure, you could have maybe guessed that based off of the coefficients, but again, many times they do not correlate. And anyway, I don't just want the answer. I want all the work. How did you replace NOBr2 with terms that are actually reactants in the overall reaction? Okay, I'll stop talking, get to that, see if you can prove, right? Prove that the rate law expression for the overall reaction is indeed this.